Hello, my name is Antti Pulkkinen and I work at the Catholic University of America and NASA Goddard Space Flight Center's Space Weather Laboratory. And in this tutorial I will give an answer to the question, why do we need more than one eye in the sky? And this refers especially to coronagraph imaging of coronal mass ejections propagating in the solar corona. Now, of course, quick answer to this is that we need two eyes to build a depth perception of the objects that we are observing. You need two eyes to get three-dimensional properties of the object that you're observing. But we will look a little bit more in detail how this plays out in terms of coronagraph imaging of CMEs. To set the stage for this tutorial, let's take a look at actual coronagraph imagery. This is imagery taken by LASCO C3 coronagraph on board Solar and Heliospheric Observatory located at Lagrange 1 point. And this sequence of images that I will be showing is for September 22nd, 2011. And let's start with the movie mode, which is part of one feature of Integrated Space Weather Analysis System ISWA that I'm using here. So what you see here is a moving object, moving structure in the coronagraph imagery. This is of course a classic signature of coronal mass ejection, a CME. And you can see that in this imagery it's moving to the right. But now what the fundamental problem here is that now, because you have only this one eye in the sky, you are actually not able to tell if the CME is moving towards the observer, towards the SOHO spacecraft, or going away from the SOHO spacecraft. Okay, and this is something that we're trying to address by using more than one eye in the sky. Alright, so let's draw a schematic illustration of the situation that we're addressing here. Let's draw a sun first here in the middle of the canvas. Right here. Let's give a little bit of color for it. Let's make it yellow, and let's use some labeling here too. I call this thing a sun. There you go. And then let's draw also the location of our first spacecraft. And let's draw one spacecraft here. Give some color for this thing also. And then let's label this thing as spacecraft C. You will see later on why I'm using this type of a naming convention for this, but for our purposes here, the spacecraft C will now illustrate the SOHO spacecraft. So what we are looking at here is now a schematic illustration in the ecliptic plane, meaning that SOHO spacecraft and the Earth and the other planets go around the Sun this way. Okay, so we're sort of looking at the Sun from above. All right. So now if we're going back here to the LASCO C3 imagery, what we're seeing here, we're seeing a CME going to the right in the LASCO C3 imagery. So let's set that also here on this canvas. So we have a moving object moving to the right in the spacecraft C in the SOHO imagery, and this is then velocity. But this is now the plane of sky velocity, so let's call it VPC. Okay. Now, what is problem here? Well, I mean, let's first discuss a little bit the concept of projection, and let's use projection operator to discuss this concept. The projection operator. Here we go. What this thing does is it projects three-dimensional vectors to a plane of sky of the observer. So let's draw again. Here's our origin, and we have a three-dimensional vector. This can be any vector. Let's call this vector v over here. Then we have observer over here, and observer observes the plane of the observer has his or hers plane of sky, which we will draw here. And plane of sky is perpendicular to the line of sight from the observer. So what the projection operator does now that it operates on the three-dimensional vector v. Let's express it a little bit more rigorously here. It operates on vector v, and what it does nothing else than it extracts the plane of sky component of this three-dimensional vector. And in our case, that projection is in the plane of sky of the observer here, and we will call this Vp, which is the velocity in the plane of sky. So this is Vp. Okay. All right. So this is the basic purpose of the projection operator. It takes the three-dimensional velocity or any other vector to that matter and projects that vector to the plane of sky of the observer. And now it's important to note that actually it turns out that the determinant of this mathematical object vanishes, which means that the inverse of the p inverse, meaning p minus 1, does not exist. Does not exist. And what this just simply means is that just by knowing the plane of sky speed, you cannot determine the true three-dimensional property of the actual, for example, the actual propagation direction. And what it means, for example, in the imagery such as one here, it means that just by observing the plane of sky velocity of the propagating CME from one spacecraft, you are not able to tell if this thing here is coming towards you or going away from you. And a little bit more mathematical expression of the same problem is here, is that now if we have the true three-dimensional propagation direction of the CME v here, it will have the projection VPC here, but we could have also the true three-dimensional propagation v going this way, and it would have identical plane of sky projected velocity vector. So just by using observations from one single spacecraft, we are not able to tell which one of these is the correct answer. Okay, so that's the sort of the fundamental problem that we need to address by means of using more than one eye in the sky. And we'll do that by adding here a couple more spacecraft to our schematic illustration. Let's put one here, and let's put some color for that, and then let's draw another one about here. Some color for that also, and let's call this one here spacecraft A, and this guy here we will call spacecraft B. All right. So of course now you will see that what's the purpose of this naming convention. The spacecraft A here of course now illustrates the location of the stereo ahead spacecraft, and spacecraft B will illustrate the location of stereo behind spacecraft. So let's now use information from spacecraft B to address the problem that we have here. So stereo behind provides us additional information by means of another plane of sky velocity of the observed movement of the coronal mass ejection in the stereo behind imagery. So it will provide us V P B, the projected velocity as seen, the plane of sky velocity as seen by a stereo behind spacecraft. All right. So now, how can we solve this problem? Let's do this in terms of the projection operator. So we have essentially now two equations here. So these are observational information, VPC and VPB. Let's express that. So we have VPC, which is in terms of the projection operator that operates on the true three-dimensional vector. Let's call this equation number 1. And then, so if we had only this information available, because the inverse of the projection operator doesn't exist, we are not able to extract or derive the true three-dimensional vector. But now, since we have two eyes in the sky, we will have additional information in terms of VPB. And yeah, this projection operator is dependent on the location of the observer. Okay, so we need to express this as a PC. And here another projection operator, PB, and it operates on the same three-dimensional vector B. And this is our equation 2. So now what we can do here is that we can combine this information to actually solve for V. So we can, what we can do here is we can sum these two equations, and if we sum these two equations, what we get, we can solve for V, and the final solution is nothing else but inverse of oops, draw a little bit better. The sum of VPC plus PB, and we will have to take inverse of that. And now, even though inverse of PC or PB alone does not exist, it turns out that the inverse of sum of PC and PB does exist. So this is a well-posed problem, and that we will multiply by the sum of the VPC and the other VPB. Okay, and that's our solution. So now, using the information from two different directions, we're able to solve for the actual true three-dimensional velocity of the CME in our imagery. Okay. So what it means in practical terms is that if we bring here the observations from stereo behind, again I'm using the ISWA here, so let's bring in these both displays at the same time and start the movie mode also for this display. So from LASCO C3 imagery alone, you're not able to tell whether or not it comes towards the observer, towards the SOHO spacecraft. But now that you have stereo behind information also available, where you see that the CME is going to the left, you can quickly determine by using, for example, this type of a schematic illustration, since the CME is going right from SOHO imagery and it's going to the left from stereo behind imagery. The actual CME has to propagate away from the SOHO spacecraft. So by using information from these two spacecraft, you're actually able to extract three-dimensional information about the propagation direction of the CME. And a little more mathematical terms, you can use the projection operator formalism. For example, the projection operator formalism to get the actual numbers for this three-dimensional velocity vector of the coronal mass ejection that you see in the imagery. And that's really sort of a fundamental reason why we need more than one eye in the sky. We need more than one eye in the sky to extract three-dimensional information about these propagating structures in the solar corona. And that ends this tutorial.